Hello everyone, welcome to this video and you are watching the video lesson on sequences. With the challenges in learning delivery posed by COVID-19, the Bureau of Curriculum Development accelerated the identification of the essential learning competencies and streamlined this further into the most essential learning competencies, in short MELCs, and each MELC is designed for a duration of 1 week. So basically, this video is just one of the few learning materials that you need to understand sequences. Are you ready? Make sure you have with you your modules or your learner's material or even self-learning activity sheets, and it is advisable that you have read all of those. Once again, I ask you, are you ready? Let's start. Before anything else, we will start with an activity entitled, What's Next? That's the Next. I'll be giving you a set of shapes, numbers, or a series of letters, numbers, and you will be identifying what will be the next of the series. Okay, start. ROYGBI. What will be the next letter? That's right, letter V. PEMDA. What's next? Yes, letter S. What if a triangle, a square, a pentagon? What would be the next? Yes, a hexagon. What if we have A1, B2, C3, D4? What's next? E5. How about 2, 12, 22, 32, 42? What's next? Yes, we have 52. Now I ask you, were you able to find pattern and get the next number? The shapes, numbers, and letters in the examples are called sequence. What is a sequence? Let us define sequence as a function whose domain is a finite set of positive integers, say 1, 2, 3 up to n, where n is a positive integer. Or it could be an infinite set, 1, 2, 3, and so on. Each element or object in the sequence is called term. So if we have this function, the domain n, or 1, 2, 3, 4, 5, is the relative position of each term. So if we have 1, if we see 1 here, that means first position or first position of the term. 2, second position of the term. 3, third. 4, fourth. 5, as fifth. If we say a sub 1 is 2, that means the first term is 2. If we say a sub 2 is 4, that means the second term is 4. A sub n, where n is 3, is 6. That means the third term is 6, and so on. So a sub n is the actual term of the sequence. Sequences may come in rule form. These are sequences stated in general rule. So in our last example, our general rule is a sub n equals to n, wherein n is the term number and a sub n is the nth term. So if we solve for the first term, we substitute 1 to the variable n. So a sub 1 is equal to 2 times 1. We get a sub 1 as 2. So our first term is 2. Next, If we look for the second term, substitute 2 to the variable n. That will become a sub 2 equals 2 times 2. So we get a sub 2 equals 4. If we are to look for the third term, we substitute 3 to the variable n. So we have a sub 3 equals 2 times 3, which we obtain 6. Our third term is 6. Our fourth term, substituting 4 to the variable n, we have a sub 4 equals 2 times 4, and we obtain 8. Lastly, a sub n equals 2n, our general rule, substituting 5 to the variable n to obtain the fifth term, we have a sub 5 equals 2 times 5. We get a sub 5 equals 10. Now, what if you are tasked to write the first 5 terms of 4n minus 4? We plotted in a table of values wherein our domain n is 1, 2, 3, 4, 5 because we are looking for the first 5 terms, and our range a sub n is what we are going to solve. Our general rule is a sub n equals 4n minus 4 because 4n minus 4 is given from the problem. For our solution, we use the general rule a sub n equals 4n minus 4. Substituting 1 to the variable n, we have a sub 1 equals 4 times 1 minus 4. Computing, a sub 1 equals 4 times 1, we have 4, and then minus 4. So we obtain 0 as the first term. Next, we use again the general rule, but this time we substitute 2 to the variable n to solve for the second term. So we have a sub 2 equals 4 times 2 minus 4. We obtain a sub 2 equals 8 minus 4, and we have 4 as our second term. Next, using again our general rule, substituting 3 to get our third term to the variable n. So we have a sub 3 equals 4 times 3 minus 4. So we have a sub 3 equals 12 minus 4. We obtain a sub 3 equals 8. That means our third term is 8. Next, we substitute 4 to the variable n. We have 4 times 4 minus 4. That is 16 minus 4. We have 12 as the fourth term. And lastly, substituting 5 to the variable n, a sub 5 equals 4 times 5 minus 4. We have a sub 5 equals 20 minus 4, and a sub 5 is 16. That means our fifth term is 16. What if we are to write the first 5 terms of 2 minus 2n squared? Take note, it is useful for us to plot these values in the table. So our domain is n, 1, 2, 3, 4, 5, again because we are looking for the first 5 terms. And we solve for the range a sub n. Our general rule is a sub n equals 2 minus 2n squared. For our solution, we will use our general rule and substitute the values 1, 2, 3, 4, 5 to obtain our first 5 terms. Substituting 1 to the variable n, we have a sub 1 equals 2 minus 2 quantity 1 squared. Take note that our power here, or our exponent 2, is only for the variable n. So that means if we substitute 1 to our variable n, 1 has an exponent of 2. So we have a sub 1 equals 2 minus 2 times 1 squared. Solving further, we have 1 squared is just equal to 1. So we don't have any exponents on this line. So we have a sub 1 equals 2 minus 2 times 1. Next, we solve first our 2 times 1 here. We obtain 2 And lastly, 2 minus 2, we have 0. So, our first term is 0. Next, using again our general rule, to get the second term, substitute 2 to the variable n. We have a sub 2 equals 2 minus 2 times 2 to the power of 2. Again, I repeat, our exponent here is only for our variable n. So if we substitute 2 to the variable n, our 2 here has an exponent 2. So 2 times 2, we have 4. Solving further, 2 minus 8, we have negative 6. Our second term is 6. For our third term, substitute 3 to our variable n. So, a sub 3 equals 2 minus 2 times 3 squared. So, 3 squared is just 9. So, 9 times 2, we have 18. So, we have 2 minus 18, that is 16. That means our third term is 16. For our fourth term, again, substitute 4 to our variable n. We have 2 minus 2 times 4 squared. So, our 4 has an exponent of 2. We solve that. We obtain 16. We solve for 2 times 16. We obtain 32. And now we solve for 2 minus 32. We have negative 30. So, our fourth term is negative 30. Lastly, for our fifth term, we have to substitute 5 to the variable n. That is a sub 5 equals 2 minus 2 times 5 squared. So, 5 squared is just 25, or 5 times 5 is 25. We solve 2 times 25. We have 50. And lastly, 2 minus 50, we obtain negative 48. So, our fifth term is negative 48. So, from the problem, write the first 5 terms of 2 minus 2n squared. That is 0, negative 6, negative 16, negative 30, negative 48. Now, how about if we are to write the first 5 terms of 3 times 2 raised to the power of n minus 1. You can try solving this. Pause this video for a while and come back here to check your answers. In our table of values, we write the domain 1, 2, 3, 4, 5 because again, we look for the first 5 terms. Looking for the range a sub n, we use the general rule. A sub n equals 3 times 2 raised to the power of n minus 1. Take note that our power n minus 1 here, or our exponent n minus 1, is intended only for our 2. 3 is not included. So, if we solve for the first term, substituting 1 to the variable n, we have a sub 1 equals 3 times 2 raised to the power of 1 minus 1. Solving first our exponent, 1 minus 1, we have a sub 1 equals 3 times 2 raised to the power of 0. And by laws of exponent, any number except 0 raised to the power of 0 is equal to 1. So that means we have 3 times 1. And we obtain a sub 1 equals 3. Our first term is 3. Solving for our second term, substituting 2 to the variable n, we have a sub 2 equals 3 times 2 raised to the power of 2 minus 1. Solving 2 minus 1, we have 1. Solving power of 1, we have 2. Solving 3 times 2, we have 6. Our second term is 6. For our third term, we substitute 3 to the variable n. We have a sub 3 equals 3 times 2 raised to the power of 3 minus 1. Solving 3 minus 1, we have a sub 3 equals 3 times 2 raised to the power of 2. Solving 2 squared, we have a sub 3 equals 3 times 4. And then solving 3 times 4, we obtain a sub 3 equals 12. So our third term is 12. Next, to find the fourth term, we substitute 4 to the variable n. A sub 4 is equal to 3 times 2 raised to the power of 4 minus 1. Solving 4 minus 1, we obtain a sub 4 equals 3 times 2 raised to the power of 3. Solving 2 cubed or 2 raised to the power of 3, we have 2 times 2 times 2, we obtain 8. So, a sub 4 is equal to 3 times 8. And a sub 4 is 24. Our fourth term is 24. Lastly, we have a sub n equals 3 times 2 raised to the power of n minus 1 as our general rule, substituting 5 to the variable n. We have a sub 5 equals 3 times 2 raised to the power of 5 minus 1. Solving 5 minus 1, we have 4. Solving 2 raised to the power of 4, 2 times 2 times 2 times 2, we obtain 16. So solving 3 times 16, we have 48. Therefore, we have a sub 5 equals 48. 48 is our fifth term. So our first 5 terms of 3 times 2 raised to the power of n minus 1, 3, 6, 12, 24, and 48. That's all for this video, and credits to Sir EJ for the PPT. I hope you learned something, and if you have some questions, clarifications, don't hesitate to contact me or ask me personally via Messenger, Honeydenil, and make sure to answer practice exercises and the activities on your learning materials.